Good day, everyone. I am Charles Van Sackey, a rising third-year PhD student in engineering and public policy at Carnegie Mellon University. And today I will be sharing with you my research on electricity system planning for productive uses of energy in agriculture. There is a problem in sub-Saharan Africa. While the subcontinent has the world's highest population growth rate, it only accounts for less than 3% of the world's electricity consumption. Access to electricity would enable sub-Saharan African countries develop by powering essential sectors such as education, healthcare, and agriculture, among others. And studies have shown that electricity access is necessary for economic and social development. Hence, the United Nations has set universal access to affordable and reliable electricity as Goal 7 of its Sustainable Development Goals. The plot on the right-hand side shows the relationship between the Human Development Index, HDI, and per capita electricity consumption. The Human Development Index is a summary measure of key achievements in areas such as health, literacy, and standard of living. Generally, countries with high HDI scores like the US have a high per capita electricity consumption, whereas sub-Saharan African countries like Rwanda and Ethiopia, indicated in red on the graph, consume not more than 170 kilowatt hours per capita. Hence, access to electricity will play a key role in sub-Saharan Africa's path to development. With off-grid technology gaining traction in sub-Saharan Africa, electrification models have been developed to determine the optimal distribution of grid and off-grid electricity supply. However, majority of electrification models and research have focused on residential demand in sub-Saharan Africa. While residential access to electricity does improve people's standard of living, studies show that most of the utility companies in sub-Saharan Africa are unable to recover their costs due to the small scale of residential demand. This is why productive uses of electricity are important. Productive use can be defined as any activity such as agriculture that generates income, increases productivity, and provides economic value through electricity consumption. Thus, productive uses serve as the means through which electrification can boost economic development. The agricultural sector in sub-Saharan Africa accounts for 30 to 40% of the subcontinent's GDP, and research has shown that improved irrigation practices through the use of technology does increase agricultural productivity. Thus, providing electricity to agricultural practices could not only aid in the cost recovery of these utility companies by increasing demand, but also it would increase household income and improve food security in rural parts of sub-Saharan Africa. As such, the agriculture sector holds great potential for productive use demand for electricity. So this leads me to the main research question we investigated, which is, how does integrating demand from smallholder pumped irrigation as a productive use impact the least cost electrification plan within a sub-Saharan African country? And to explore my research question, I needed an electrification model that is open source, uses geographic information systems data, incorporates productive use, and has an array of technologies for electricity supply. With this accommodation for productive use, Onset proved to be the most suitable model to explore my research question, and the Onset model is highlighted in yellow at the bottom of the table. So the open source spatial electrification toolkit, or Onset, uses GIS data in electricity system planning to determine the most cost-effective technology deployments to achieve universal access in a country or a region by 2030, and its 7 supply options include grid connection, standalone diesel and PV systems, diesel, PV, wind, and hydro mini grids. And this flowchart shows the flow of information regarding integrating this agricultural demand. And here we are looking at agricultural demand in the form of small-scale pumped irrigation integrating it into the onset model. And so the parts contained in the dashed boundary are in the onset model, and the parts external to the dashed boundary are the necessary input data. I will now discuss the input data for the model. To begin with, onset uses population cluster dataset from the World Bank Global Electrification Platform website that contains relevant data such as the number of households, whether the cluster is rural or urban, and technical data such as the global horizontal irradiance and wind speed, among others, for each cluster in a given country. And a cluster can be understood as a group of households, which for our case study on Ethiopia can vary from as few as 2 households to as many as over 1 million households. And they're the units into which a country is divided for processing into onset. Additionally, onset uses electrification tiers as different target levels of residential electricity access for a cluster, depending on whether the cluster is rural or urban. And further documentation from the World Bank GEP website recommends the tier of electricity access for rural and urban areas in a country. As much as using these electrification tiers to estimate residential demand reduces computation time and the complexity of our model, it does pose a limitation on the model because it does not capture the varying energy demand profiles across different household types and users. So the focal point of my presentation today is the agricultural demand piece highlighted in red on the chart, which is our contribution to the existing onset model. So in Ethiopia, the Ministry of Water, Irrigation, and Electricity has partnered with the Agricultural Transformation Agency to prioritize the cultivation of certain crops in certain woredas in Ethiopia to boost the country's agricultural outputs and double the income of farmers in the next 5 years. And for the purposes of my presentation, you may think of a woreda as a county in the United States context. The woredas shown in yellow are the maize prioritized woredas, whereas those in orange are those prioritized for wheat. And together, maize and wheat farmland accounts for about 13% of Ethiopia's current cropland. So I use this map for the spatial distribution of agriculture demand in Ethiopia, and thus the results I will show will be focused on clusters located in the maize and wheat prioritized woredas only. So to estimate agricultural demand, I used cropland data from the MapSpam repository assembled by researchers in the International Food Policy Research Institute, and the cropland data is generated from their spatial production allocation model, which uses land cover data to determine crop distribution around the globe. The cropland data set provides me with the hectares of cropland for a given crop throughout a country, which is used to estimate the alpha term in the equation written at the top. And the Copernicus land cover map was used to find the percent crop cover signified by the omega term. Thesan polygons were used to geospatially characterize the clusters, the area of which is symbolized by the A sub C term. And the product of these terms gave us the approximate area of a crop in a given cluster. So next, we used irrigation demand data from an exogenous model that is based on the aquacrop FAA model, which essentially is used to estimate improved yield due to pumped irrigation, and then determines the total electricity demand to pump groundwater. Hence, this data set gives us the electricity demand per hectare of cropland for a given crop, which is indicated by the D sub ij term, and the irrigation requirement data set assumes fixed levels of soil fertility throughout a country, which poses yet another limitation on the model, since soil fertility in a country varies widely based on many factors such as the use of synthetic fertilizers and soil management practices. Using these data sets, we were able to estimate the agricultural demand in each cluster, which amounted to 2.25 terawatt hours, and the total energy expended on irrigation per ton of maize and wheat produced per our estimate is about 76 kilowatt hours per ton. So having estimated electricity demand, ONSET then uses energy system specific data to calculate the levelized cost of electricity for the 7 supply options, which here are categorized into grid, mini grid, and standalone. And the model then selects the lowest LCOE technology for each cluster as the optimal electrification mix for the country. So for this project, as I mentioned, we used Ethiopia as a case study, and Ethiopia is a country located in East Africa with a population of over 100 million people. And the government of Ethiopia aims to achieve 100% electrification by the year 2030. And so since Ethiopia's current electrification rate stands at 44%, it does serve as an excellent candidate for electricity system planning. So in our case study, we used 2 demand scenarios to capture the associated uncertainty of average usage patterns. As a reminder, we expanded the residential demand estimates to include potential demand from small-scale pumped irrigation, which we refer to as agri-demand. Within each of these scenarios, we have a base case with only residential demand and an agri-demand case that incorporates potential demand from small-scale pumped irrigation from wheat and maize specifically. As mentioned earlier, we only considered maize and wheat in the study because they were the only crops with both irrigation demand and cropland data sets available. So our model results. The maps shown here display the optimal electrification mix in the agricultural clusters for the high demand scenario. We see that grid indicated in black, standalone PV in red, and a bit of PV mini grid indicated in green are the main technologies used in the high demand scenario. There was a 34% increase in demand from 6.7 terawatt hours to about 9 terawatt hours in the agri demand case in the high demand scenario within these agricultural clusters. And this amounted to a total overnight capital cost of $9.8 billion to meet this total demand. Our radar level data showed that the average irrigation requirements for maize is 3,200 kilowatt hours per hectare, whereas that of wheat is only 2,295 kilowatt hours per hectare. Now, although wheat has a lower irrigation requirement in Ethiopia, almost 80% of the clusters in wheat prioritized warriors were actually electrified by the grid. Now, based on the data sources for estimating agricultural demand that we used, we actually determined that there are 7,000 more hectares of wheat cultivated than there are of maize, which ultimately led to the wheat clusters being primarily electrified by the grid. And the tables on the right show the percent of people living in these agricultural clusters electrified by the respective energy systems. And in the low demand scenario, we see that grid and standalone PV are the main technologies used in this scenario, and overall demand more than doubled from 1.02 terawatt hours in the base case to 3.27 terawatt hours in the agri demand case, amounting to a total overnight capital cost of $5.2 billion. And again, the tables on the right are showing the percent of people in these clusters electrified by each technology. Now, whereas there were virtually no transition in supply options in the low demand scenario, there was a transition in supply options for about 121,800 agricultural clusters in the high demand scenario. One of the main drivers of these transitions is the change in electricity demand shown in the histograms on the right for the agricultural clusters. Specifically, our results show that over 51,000 wheat clusters transitioned from standalone PV or photovoltaic systems to the grid connection, whereas only 43,000 maize clusters made the same transition. Now, given that the median increase in demand for the wheat clusters that transitioned from standalone photovoltaic or PV to grid was 236% increase compared to this 175% increase for their maize counterparts, we concluded that wheat drives the transition in energy systems more than maize does. So for our analysis, we used the levelized cost of electricity of each energy system as a proxy for electricity affordability. In the figure on the left, we observe that LCOE ranges from 1.8 cents per kilowatt hour, corresponding to clusters that had pre-existing connection to the grid, to 38 cents per kilowatt hour for clusters electrified via photovoltaic mini-grids. The transitions in energy systems, specifically those from off-grid to grid electrification, caused a median reduction of 68% in capital cost. These reductions in capex, in turn, resulted in an up to 95% decrease in LCOE as visualized on the right-hand side. Hence, future work that aims to determine the cost recovery implications of irrigation as a productive use for utility companies and the affordability of electricity for agriculture would need to focus on tariff structures that reflect the difference in cost of supply to farmers of different crops. So to conclude, our research shows that contrary to the extant literature on electricity system planning in sub-Saharan Africa, rural electrification does require a non-trivial investment in grid extension and densification, specifically up to $9 billion in Ethiopia. Secondly, reductions in LCOE driven by energy system transitions in wheat clusters would require a change in pricing or the tariff structure to enable cost recovery for utility companies and mini-grid developers. And finally, further studies would be necessary to determine the willingness to pay of these new electricity customers from the agriculture sector and its implications on utility companies. So that brings me to the end of this presentation. Thank you very much for your attention.